Today we're going to talk about rotational motion. We want to talk about rotation. First of all, we're going to talk about rotational variables. And I think we already began this discussion earlier in the semester. But let's recap. So when we're talking about rotational motion, we want to talk about our angles in radians. How do we define an angle measure in radians? Right, here's a piece of pizza. What's the angle measurement of this wedge? Given it came from a circle of radius r, and there's S amount of crust. So what's our angle measurement in this case? Matthew, what do you think? How do radians work?
Isn't it just simply like a fraction of a radian, or they basically say uh like it's basically kind of on a numerical scale of like like 1 radians, 2 radians, 3 radians, and so on and so forth.
Right. So if it is, so radians are a number, but if we know the radius of the circle and the length of the arc, right? This is how we define an angle measure in radians, right? It's the ratio of these two things. All right, so this is just a little bit of review. So this was probably mentioned, for maybe a week in high school algebra 2, and then you forgot about it forever. Um, but now that we're doing physics, we need to actually remember this definition. So if we have something rotating, what we mean by rotation is that the angle measurement is changing. Right? So if we have something at a fixed center and it's rotating, then we don't want to just measure the angle. We want to measure how the angle's changing. In other words, we'd like to be able to take the derivative. So the symbol that we use for the time derivative of the angle is omega, and this is angular speed. Now, using our definition of the angle in radians above, we can take the derivative of this definition. So, assuming we are staying on a circular path, the radius isn't going to change, so we can actually factor that out. Right? And what might we call the change in this arc length over time? Right, Zachary, what might we call the change in this distance over time, ds dt? What's the derivative of distance with respect to time? Velocity, exactly. So the angular velocity, right, the rate at which the angle is changing, is related to the linear velocity. That is the rate at which you are increasing your distance as you go around the circle. We can make a similar argument if we want to take the derivative of the angular speed. Right? We might expect that it has something to do with the linear acceleration, the same way that the angular speed has to do with the linear speed. And we're going to go ahead and call this alpha. So similarly, if we already have a definition of omega, with respect to v and r. So we can go ahead and take the derivative of that. And if we're staying on a circular path, that radius is constant. We can pull that out. And sure enough, what is the derivative of velocity with respect to time? That is acceleration. 100% correct. All right, so that's the kind of relationship that we want here. Let's see what happens when we apply this relationship to our kinematic equations. So here's our kinematic with respect to distance. So 1/2 at squared plus v naught t plus x naught. For the moment, we're going to consider the one-dimensional case here. If we take this whole equation and divide it by r, then we get x over r equals 1/2 a over r t squared plus v naught over r t plus x naught over r. And using our relationships in green in the corner, well, the distance over the radius is just the angle. The acceleration over the radius is the angular acceleration. The initial velocity over the radius is the initial angular velocity. And the initial position over radius is our initial angle. Similarly, if we start with kinematic number 1, divide the whole thing by r, then we get an equivalent kinematic for angular coordinates. And lastly, if we take our time-independent kinematic equation, divide the whole thing by r squared, so v squared over r squared is omega squared. V naught squared over r squared will be omega naught squared. And then for the second term, we'll take one of the r's in the denominator and make a over r. which is alpha, and the other r will go to delta x over r. Call that delta theta. There we go. So I think we covered this briefly earlier in the semester. If you have any questions about rotational variables and how we can transform our kinematic equations into rotational kinematics pretty easily. Anybody have questions or comments on this?
Why did you square R for the second one?
For the orange one?
Yes.
Since we had v squareds in the equation, we knew that v over r is going to give us omega. So v squared over r squared, right? That'll give us omega squared, because you need one factor of r to transform each factor of v, right? So 2 factors of v means you need 2 factors of r.
Okay.
Okay. Good question, though. All right. Any other comments or questions? Okay. So these kinematic equations work exactly the same as our linear kinematic equations. So if you want to say let's say that you have a mechanical hard drive, and you may know that your mechanical hard drive has a rotational speed of 7,200 rotations per minute when it is active. When you go to shut down your computer, it takes 3 seconds for your hard drive to spin down, like to slow down to a stop. How many rotations does your hard drive platter make during the shutdown procedure? Well, we're going to convert 7,200 revolutions per minute into radians per second, because we can't do physics on revolutions per minute. We need it in terms of radians. So first of all, there are 1 minute has 60 seconds. So our units of minutes go away. And also, there are 2 pi radians in 1 revolution. So we have what? 240 pi radians per minute per second. Okay, and this is our initial speed. If this is our initial speed, then we can use this kinematic here and say, well, if it takes 3 seconds to spin down from 240 pi radians a second down to 0 radians per second, that means that the acceleration that we are experiencing is going to be minus 240 divided by 3, which is minus 80 pi rads per second squared. And now that we've got everything, we can plug it into our purple kinematic here and say, well, then the angle that we rotate through on our way to spinning down is 1/2 80 pi 3 squared plus 240 pi. Oh, sorry, this should be a negative, and there should also be a factor of t here. That's my bad. Okay. Plugging that into the calculator, I get about 360 pi radians. And if we wanted to convert that back to revolutions, right, that's 180 revolutions. So in the 3 seconds it takes you to turn your computer off, the platter on your mechanical hard drive spins 180 times around. Any questions or comments on this so far? All right. Let's go a little more in depth. What happens when we apply this same sort of reasoning to Newton's second law? So what I'm going to do here actually is I'm going to take the cross product of both sides of the equation with respect to the radius of a circle. So if we are engaging in circular motion, there's our radius. So now we have the sum of F cross R equals M A cross R. Now, cross products, we could totally do this derivation with cross products, but I'm going to save that for your Calculus 3 class so that I don't ruin the surprise. Instead, we're going to use a property of cross products to simplify this. The magnitude of A cross B, so A cross B is a vector, and the magnitude of A cross B is equal to AB sine theta, where theta is the angle between A and B. Actually, since we're using theta for something else, let's use a different beta, right? Where where beta is the angle between A and B. And the direction of A cross B is given by the right-hand rule. I'm not going to go too much in the right-hand rule during lecture. I do suggest that you look up a YouTube video of people trying to contort their hands to explain it. For our purposes, it will suffice to simplify this. So we are going to we're going to consider a radius and a force and if this force would tend to make the radius arm rotate counterclockwise, then F cross R is in the positive direction. And if a force would tend to make the whole thing rotate in a clockwise direction, we're going to call that a negative. We're going to say F cross R is in the negative direction. This is the same answer that the right-hand rule will give you. It's also the same answer that you'll get if you actually do the cross product out. But this will suffice for now. So we're going to take the magnitude of our cross products on both sides. Do we have questions or comments on this part of the procedure? You mean this graph in the bottom right? So if you imagine like holding a pencil out straight, right? Holding it at one end. If you push on the tip of your pencil with the other hand, say like this, you are going to tend to cause the entire pencil to rotate in a clockwise direction. By convention, rotations in the clockwise direction are negative. So in this case, F cross R right is in the clockwise direction, and we're gonna call that the negative direction. Yeah, so clockwise and counterclockwise, that's why we're going to talk about it here. If we were being more precise, we would talk about rotational axes pointed in the positive or negative z direction. That is another way to think about this. So if F cross R points in the positive z direction, that's the same as a counterclockwise rotation. So that is a positive um, cross product. All right, everyone remembers we briefly covered cross products at the beginning of the semester? Did that answer your question, Jaden? Cool. So now that we're here, we're going to use um, a relationship between linear and angular coordinates. Right? So if alpha is our angular acceleration, and the magnitude of that is our linear acceleration divided by the radius, we could also say that alpha times r is equal to the linear acceleration. And that's what we're going to say here. Oh, first, actually, we're going to split this into two parts. So if we have a radius and a force, and they are at some angle to one another, we can split them into a part that is parallel and a part that is perpendicular. Right? We've been doing that all semester as we decompose vectors into x and y components. We're going to do the same here, except we're going to decompose it into components that are parallel to the radius and perpendicular to the radius. So that lets us get rid of this sign bit. So now we have the sum of forces perpendicular to the radius equals ma, acceleration perpendicular to the radius. In other words, acceleration that is along the edge of the circle. And now we're going to replace linear acceleration with alpha times r. And we're going to rearrange this just a little bit. Anyone have any questions or comments on this algebra so far? Because it's about to get weird. Okay. Now that we're here, we're going to make some renaming. We are going to take this part on the left-hand side of the equation, this perpendicular part of the force times the radius. We're going to rename that torque. Right, so last week we did some analysis with momentum, and the quantity mass times velocity just kind of popped out of our analysis, and we renamed it momentum. So in that spirit, this quantity F, perpendicular force times R, that pops out, we're going to rename that torque. We're going to take this mr squared here, and we're going to rename that as well. We're going to rename that the moment of inertia. And lastly, we've got our angular acceleration. So this is Newton's second law for rotation. So you may ask, well, what happens to the part of the force that was parallel to the radius? Well, if you pick up a pencil and you try to push on the tip of the pencil, right? That's a force that's parallel to the pencil. You're not going to rotate the pencil. Instead, you're just going to move it. So that's what we notice here. So we have split up the force into a part that's perpendicular to our radius and a part that is parallel to our radius. The part of the force that is parallel is going to tend to translate or move the object. And we've already studied that in chapter 4 and 5, right? That's our regular Newton's second law all over again. So it's only the part that is perpendicular to this radius that does something new. And the part of the force that's perpendicular to the radius tends to rotate an object. And so we have, if we sum up all of the tendencies toward rotation, all of the torques on an object, we will be able to get its angular acceleration. And instead of mass resisting it linear acceleration, it's the moment of inertia that provides the resistance to angular acceleration. We have any questions on this bit? All right, so far so good. Let's look at the energy, right? If we have an object undergoing circular motion, once again, we know that there's an energy associated with the speed of the object. Okay, and we write that the kinetic energy of this object is equal to 1/2 mv squared. We're going to make a substitution, though, because we want to talk about the energy of rotation. So instead of writing down v, we're going to write down omega times r. And then you may notice that this bit here, this mass times radius squared, that's exactly what we called the moment of inertia. In fact, we're going to be more specific. The moment of inertia for a point mass is just mr squared, where r is the distance from the center of rotation. So the kinetic energy that is associated with a rotating object is just 1/2 I omega squared. Right? This, by the way, completes the set of energies that we are going to look at this semester. Right? So now our total list of energies, I'm going to call this capital R, by the way. So the total list of energies that we consider in this class are the kinetic energy, the gravitational potential energy, the spring potential energy, and now the rotational kinetic energy. These are not all the kind of energies in the world, but these are the 4 kinds of mechanical energy that we consider in this class. Any questions or comments up to this point? All right, so far, all we've done is some variable substitution based on the definition of radiance. Now we actually get to do some interesting integrals. So I hope you all brought your calculus hats this morning. Now, we said that for a point mass, the moment of inertia is equal to the mass times the square of the distance from the axis of rotation. You may have noticed that most real objects do not concentrate all their point into a mass. So how can we deal with real objects that are undergoing rotation? Anybody have a thought? I think we could do an averaging thing. We could, yeah. Ideally, if we could, maybe like with Newton's second law, if we could pretend that all the mass was at the center of mass, would that work? I mean, that's a reasonable suggestion. So let's investigate that. We'll start with a spinning disk. So we have a disk, and it is It's got it's got some radius. It also has some small thickness. Right, so we'll call the radius capital R for the moment. So we'll say it's got some thickness, which we'll call maybe H. It's got some total radius. And it's got some total mass. Where's the center of mass of a disk? Yeah, um, that's exactly right. The center of mass of the disk is at the geometric center of the disk. 100% correct. So if we are trying to spin the disk around its center, if it was fair to pretend like all of the mass was at the center of mass of the thing, then what would we expect the moment of inertia of the disk to be? Right, we're rotating it around its center, just spinning it. And the center of mass is also at the center of rotation, which kind of implies that this R is 0, which means that the moment of inertia of the thing should be 0. But that means that any attempt to spin it should result in an angular acceleration of infinity, right? Because the angular acceleration will be the torque over the moment of inertia. So maybe not all of us have played with tops or spinning things, but I think we can all agree that an angular acceleration of infinity is probably not it. Probably not what we're looking at in a real disk. So even though treating the object as if its center of mass had all the mass, that's a really reasonable strategy. It leads us to a conclusion that we know is impossible, right? We cannot have infinity acceleration. So let's instead let us view this this object, right? And we often refer to real objects as extended objects. That is, they have both mass and dimensions. They extend in the 3 dimensions. So for an extended object, let's, instead of making a simplifying assumption, let's treat it as made up of an infinity of point masses. So if this disk is actually made up of a whole bunch of little point masses, we know how to deal with each individual point mass. The question is, how do we add up infinity point masses? How do we add infinity things, people? That's exactly right. That is what calculus was made to do. So we're going to say that maybe the total moment of inertia of this thing is equal to an integral, where an integral just means add up an infinity of really tiny things. And it'll be the moment of inertia of each itty bitty piece. Right? Well, each itty bitty piece is going to have a moment of inertia equal to the square of the radius from the center, and I'm going to use little r here. So big R is the total circle, but little r, that's going to be the distance between the center and some arbitrary point, but that's not all the way to the edge. So the moment of inertia of each of this little bitty piece here is going to be equal to the square of its radius from the center of rotation times however much mass is in that itty bitty piece. So how do we know how much mass is in that itty bitty piece? Anybody have an idea? Morales or Cruz or Sorka? Any idea? How do we get at the amount of mass in a little differentially small volume? It's okay. I don't know is totally a legitimate answer. We do have to make a little bit of an assumption here. If we have a uniform object, then its density will be the same everywhere in the object. So if we know the total radius of this disk, we know its total mass, and we make the assumption that it's got a uniform density, then the density of this object is just mass over volume, and the volume of this kind of thin cylinder is pi r squared h. So that lets us do a little better here. So we have r squared density times a differentially small volume. So we're getting better. Right? Now at least we're in spatial coordinates, which is something we could potentially integrate over. We can do a little bit better here. Since we've got a disk, we know what the volume of this thing is. So we could actually take the derivative using a little implicit differentiation here. So the volume of any cylinder is going to be pi r squared h. So the derivative of the volume, right, assuming that it's of constant thickness, right, and that pi is a constant, we just have to take the derivative of the r squared bit. Did I lose anyone from here to here? So this gives us the product rule. Um, it was actually not even the product rule, since there was only one variable in here, which was r squared. From here to here, this was implicit differentiation. Don't worry, this is totally going on YouTube. In fact, I'll probably do a short with a couple more examples of this sort of integral. All right. Now we can take our expression for dv, plug it into this integral we've been working on. So 2 pi h rho r cubed dr. All right, and finally, we're at a point where like this looks like something we could actually integrate, right? We could totally integrate over the radius, right? And then we just have to set our limits, right? We set it from r equals 0 to r equals big R. And we factor out all these things that are constants, right? 2 is a constant, pi is a constant, the height is a constant, the density is a constant. And then we can integrate from 0 to r, and we do that because we're going to catch all of the points if we do it that way. All right. So now somebody tell me, what's the integral of r cubed dr? R to the 4th over 4. Perfect. We'll evaluate that at 0 and big R. 2 over 4 is a half. Big R to the 4th. And now that we've gotten all this way, we're going to substitute our expression for rho back in, so that we can talk about this thing in terms of its mass instead of in terms of its density. Right, and we get an h cancel off, we get the pi cancels, we have an r squared in the denominator, so that cancels there. And after all of that work, we get 1/2 mr squared. So we started with an intuition that maybe we could pretend that all of the mass in the disk was at the center of mass, but we ended up with this result that's kind of like saying we could have pretended that all of the mass in the disk was in this thin hoop at half the radius. So that's an interesting result. How many people just threw their hands up in the air when it ended up being such a simple expression at the end? So Wikipedia has a really good list of these results for a variety of different shapes. So if you just search wiki moments of inertia, you'll get a nice list. It'll tell you about the moments of inertia um, for lots of different kinds of extended objects based on rotations of axes and different points. But in general, these integrals can get a little messy, right? And this integral was for a disk, which is a relatively simple object. What if the density isn't constant? Great question. As long as we can approximate some function of the density, like if we can say the density, um, so if instead density is maybe some function of r and theta, then we leave it inside the integral. The integral becomes more complicated, but not impossible. Right? So we could have, so from here, if we did not have a constant density, we could instead say that we have maybe a triple integral. 2 and pi still come out, 2 pi still comes out of the integral. But then we have something like, rho of r theta rho cubed dr d theta dh. And then we have to do these integrals separately, and it becomes a little bit more of a pain, but not that much more. I'm out. Right, but this is when if you have a non-constant density, this is frequently a good time to pull out your integration by parts skills and go to town. Okay, now that we've got this kind of understanding that real objects can also have a moment of inertia that's well defined, what I would like to do is go over one of my favorite conceptual questions. So let's imagine we have a ramp and we are doing a race. And at the top of the ramp, we have a cylinder. We have a hoop. And we have a, say, a sphere. Okay. So all three have the same mass and same radius. The question is, which one gets to the bottom of the ramp first? Whichever you believe in the most. If only that were true. All right, so we have a vote for the sphere. So on 3, everybody type in the chat the shape that you think um, will hit the bottom first, and same is also an option. So on the count of 3, 1, 2, 3. Okay. A lot of people saying same, a lot of people saying sphere. Okay. Well, let's do the math and see what we get. Let's start with the thin hoop, since that's the easiest. So for the hoop, all of the mass is at a distance r from the center of the axis of rotation. Right? So all these objects are rotating about their geometric center. So for the hoop, all of the mass is at radius r. So its moment of inertia is equal to mr squared. For the sphere, there is a nice integral to be done here, but for the moment, we're just going to look it up on Wikipedia. So and by sphere, I actually meant ball. So in common speak, we say that these are the same, right? Sphere and ball. But to a mathematician, a sphere is a thin shell with nothing in the middle, and a ball is a solid object all the way through. And for the moment, I'm just going to look on Wikipedia to get this moment of inertia. And it's 2/5 mr squared. And then lastly, the cylinder. We did that calculation on the last page, so we know that the moment of inertia is 1/2 mr squared. Okay. So there's a way to kind of restate this question to make it a little simpler. We want to know which one gets to the bottom of the ramp first. But that's the same as asking which one is moving fastest when it gets to the bottom of the ramp. Yeah? So whichever one's moving fastest is going to have taken less time to get down there. And we can use conservation of energy to calculate this bit. So if they all start at the top of the ramp, they all start a distance h above the ground. So we're going to say that situation A is them at the top, situation B is them at the bottom. So the energy at A is going to equal the energy at B. So we're going to have mgh equals, and at the bottom, they're going to have energy both, they're going to have translational kinetic energy because they're moving, but they're also going to have rotational kinetic energy because they're spinning. So we will have 1/2 mv squared plus 1/2 I omega squared. And we can do a little bit better because we know that omega is the same as v over r. So we're going to go ahead and make that substitution. which means that we can factor out a v squared. And we get 1/2 m plus 1/2 I over r squared. So for the hoop, I is just mr squared. So we have mgh equals v squared times 1/2 m plus I becomes mr squared. The r's cancel. So we have a 1/2 m plus a 1/2 m. That's just m. And we get the velocity equals square root of gh. For the ball, we get mgh equals v squared, and then we have 1/2 m from the translational kinetic energy, and the moment of inertia is 2/5 mr squared. So again, the r squareds are going to cancel, and we get plus 1/2 times 2/5 times m. Well, a half of 2/5 is 2/10. So when we add these together, we get 7/10 m. The m's will cancel. And now we have v equals square root of 10/7 gh. And then lastly, for the cylinder, we have our moment of inertia is 1/2 mr squared. So we get mgh equals v squared 1/2 m plus 1/2 m, where again the r squareds cancel. So we have an m in every term, so that cancels, and we get 3/4 inside this parenthesis. So our velocity is equal to 4/3 gh. So I will leave you to check this, but 10/7 is just a little bit bigger than 4/3. So the ball is going to win the race down the ramp. And we know that because it will be going fastest at the end of the ramp.